Let's now see how we can implement and train neural networks. We start with the simplest neural network, which is a simple neuron. That would be this function. So if you look at this, it just adds a sigma, a function sigma, on top of the linear model or linear layer. And this sigma is going to be a nonlinearity, a nonlinear function that maps R to R. And a very popular choice for this is the so-called rectified linear unit. Here's how you can create it in PyTorch. So this creates a ReLU object or a ReLU layer, and I can apply it to data. Let me create, for example, some points here. And so to apply this function to the data, I just write something like this, and then let's plot this. You can see it's 0 for the negative values, and just linearly goes up. So this sigma mathematically would be equal to the max of 0 and x, if you think about it. Okay, so now let's recreate the data to be the output of a neuron rather than a linear model. And see if we can recover these true parameters. So recall that this is how we created the data from a linear model, where this W contains both the bias or the intercept and the weights of the linear part. And so all I need to do is apply the sigma, which is just the ReLU module, or the ReLU function. And so that gives me this y. Now let's try to train the neuron. So we have the linear module, or the linear layer, and the ReLU module. What I'm going to do is I'm going to create an optimization object of type SGD, and then I'm going to pass the parameters of the model. The parameters of the model are the same as the linear model. So just we have a weight vector and a bias. The rest is almost the same, except that now we apply the linear model first and then apply sigma. And so that creates our prediction. And then we compare it with y. This is a vector of the same length as y, both of length n. And this is the loss. So we zero out the gradient. We compute the loss at the current value of w. This updates the gradient, and this moves the weight. Let me try to run this. Okay, it was rather slow, but you can see that the loss is decreasing, and we end up having roughly the correct parameters. What is worth noting is that I need to take a lot more iterations. So it's like 5,000 iterations versus the about 100 that I took in the case of the linear model. The other interesting feature of this is that we don't always converge, or the loss does not always decrease. So if I change the seed, you can see that it's mostly stuck. So you can try running it more for more iterations. But sometimes it goes down like this. Majority of the time it goes down. The other interesting thing to note is that sometimes we can improve the convergence by increasing the step size. If the step size is already below the optimal value. So you can see it went down further. The loss went down further. You can even increase it more. Even more. So this is about the limits. See, we no longer converge. Okay, so that's something to consider. The step size matters. Okay, let's try to improve our design a little bit. Instead of writing the composition of functions every time, we can use this module nn.Sequential to form basically a function or a module that's a composition of two functions. So if I pass this linear module and the sig, so what it does is that it applies len first and then sig second. So it's just a function composition. So this object that I defined as a neuron is really a neuron, just applies a linear layer and then applies sigma. The other change that we made is that instead of passing the parameters explicitly as a list, we call this parameters function on the neuron, and it just creates a generator, which is like a list basically, but more efficient, of all the parameters in the model, which will be these two. And the other change is that instead of just applying that composition, we now can apply the neuron directly. So this cleans up the code nicely, and I can just later change the implementation of this, and the rest would basically be the same. So this should perform the same operations if I run it. Consequences of loss values. So you can see we ended up at the same location as we were before, so we did the same operations. We can also check the final estimated parameters of the neuron by iterating through the parameters here. And you can see that the weight vector is as what we got before, and the intercept or the bias is close to what it should be, which is -1. So let's have a final improvement, version 3 of the same neuron. So we can encapsulate everything into a Python class by defining a subclass of nn.Module. So we define a class neuron with capital N by defining it as a subclass or a child of nn.Module. So as you can see, nn.Module is the base class for all neural network modules. Your models should also subclass this class, and it can contain other modules and so on. So it has an init method or function, as all classes in Python have, and we call the init function of the parent. This is standard Python. And then we create a property, a simple neuron, which is basically the composition of a linear module and a ReLU. The composition is made by the nn.Sequential. Basically, we just combine these lines and get rid of the intermediate object. So that defines a property that contains our neuron, and then all these nn.Module classes, they have a forward method or function that you can redefine. So this takes self as usual. The object that you're gonna call this on is going to be passed here, and then you can pass other parameters here. I can pass x, for example, and it will basically will be called whenever we apply the module like a function. So here I'm printing something, so you can see I can create an instance of this class by calling the constructor of the class, basically. So neuron, and then it creates this object model, and then when I apply model to x, this is gonna for us compute the value of the module or the value of the neural network on x. But basically what it does is that it calls this forward method. You can guess what would happen here. So if I run this, it just prints forward pass not implemented. It doesn't magically compute things. You just have to implement this forward function. Okay, so how do we implement the forward pass in this case? It's simple. We just apply the neuron that we created and stored in the object to x and return the result. So what it does is that it calls the forward pass of sequential, which then calls the forward pass of the linear model with the data. And so we calculate the linear model. And then the sequential also calls the forward pass of the ReLU. So we pass it through the ReLU, and that would give us the output. So we calculate the composition of the two. Now if I run this, you get that the model X has some valid output. So apply model to X, this would be the output, which you can try to verify. Okay, so now this is the final version of our neuron training. So we created the neuron here via this line. So now I create the SGD optimizer object, and now here just apply the model to X. This calculates the basically output of the model on X, and the rest is the same. Okay, so I've run this final version, and you can see that the output is exactly the same as what we had before. And that's it for training a simple neuron in PyTorch.